In this lesson, I'll demonstrate how to find the domain and range of a function, both graphically and algebraically. We've already defined the domain and range of a relation. If you recall, the domain of a relation is just a set of x values, and the range is a set of y values. When we have a relation that is a function, the domain is a set of x values for which the function is defined. And the range is a set of corresponding y values in that function. Graphically, the domain is the set of x values for all the points contained on the graph. And the range is just a set of y values for all points contained on the graph. I'll go over a few examples to show you how we find the domain and range given the graph of a function. The first example is a graph of a parabola. Notice that I have two axes drawn off of the graph. In green, I have a copy of the x-axis, and in red, I have a copy of the y-axis. I use these to find out what are the values of x and y that are contained on the graph. To find the domain, we always read a graph from left to right, and we want to find what is the starting point and the ending point on the graph from left to right. Because this graph is a continuous graph, there are no stops or gaps in it. We're going to have one interval that represents the domain and one interval that represents the range. What I like to do is think about drawing down from the ending point on the leftmost point of the graph, which understand there's really no ending point because that arrow represents that it continues indefinitely. And so when I get down to my graph, I'm going to draw that with a left arrow to indicate that this really goes on indefinitely to the left. And in the same way, my ending point to the right, so think about superimposing the graph beginning and end to this copy of my x-axis. When I come down to the rightmost point, I also will put an arrow because the graph continues indefinitely to the right. So my domain is a set of x values contained between those 2 points, which because it extends indefinitely to the left and right, my domain is negative infinity to infinity. To find my range, I'm going to superimpose my graph onto this copy of my y-axis. The range, or y values, are read from the smallest to largest, which in this case is from the bottom to the top. The bottommost point on my graph is at this vertex of this parabola, which that is at the value 2. Now this is an actual point on the graph, so when I superimpose it to my copy of the y-axis, I'm going to put a closed circle because that is actually a y value contained on a point on the graph. This is a continuous piece, so where does this end? It ends up here at the top, which is represented with an arrow. And all points between the 2 and the arrow are part of the graph. Now because the 2 is included, I can use a bracket at the 2. So this interval is written from a bracket 2. Continuing infinitely in the positive direction is infinity. Example 2, I have 2 distinct pieces to my graph. I have a line segment going off to the left, or really a ray going off to the left, and then part of a polynomial function continuing to the right. It doesn't really matter the shape of the graph. Notice this is a function. It does pass the vertical line test. But to get my domain, I'm going to project down the starting and ending points of each of these pieces onto this copy of the x-axis. So my leftmost point over here is the arrow. I'm projecting it down, and we'll draw an arrow on this copy of the x-axis to represent that piece continues indefinitely. Then this piece of the line that I have, I'm going to drop it down, and it's at the x value of 0. But for that particular piece, it's an open circle at 0. But then notice my second piece picks up also at this value of 0, but it has a closed circle. So whenever I come down to my x-axis, I get to include it. Right, all I'm trying to do is find what are the values of x that are contained on this graph. And now where does this rightmost piece end? Well, over here to the right with an arrow. So whenever I project it down, I'm going to put an arrow on my graph. And so all of the pieces contained between negative infinity to infinity are included on my graph. Why did I not stop at that 0? It's because 0 is now part of the graph. If both of those had been open circles, then 0 would not be part of that interval. And so I'd have to do negative infinity to 0 with a parentheses, union 0 to infinity to show that I'm excluding it. But 0 is actually included, so all the numbers between negative infinity and infinity are included. So my domain is negative infinity to infinity. My range, I read the graph from bottom top. So the bottommost point on my graph is this vertex down at negative 10. And it is an actual point, so I'm going to include it with a closed circle. And where does this graph end? This was a little bit more complicated to think about. I have a few ending points, but notice that even though one piece of this ends here, the other piece of it is still continuing, right? So these y values are really just duplicated. So any of these y values that are duplicated, I don't need to include or separate off from my range because all of them are already included in the values. The ending point for this particular one goes up here to infinity, right? It's an arrow that continues indefinitely. Now for my other piece, this line, notice again that these values are already included somewhere else for the y values. So those are just repeating the y values that I've already included. And so my domain is going to be everything from negative 10 to infinity. In example 3, I have a half line and then a line segment. So if I'm finding my domain, I'm thinking about moving from left to right. What are the values represented on these different pieces of the graph? And the leftmost point I see is this line that extends off to the left. So I'm going to project it down and draw an arrow there to show that it's continuing. Where does this piece end? It ends at an x value of 1, which is not included. So I'll put an open circle. But then the second piece picks up at 1, now with a closed circle. So I'm going to close that in. And this ends at the rightmost point, which is at an x value of 4. And it's closed on the graph, so I'm going to put a closed circle down here. So notice that everything between negative infinity to 1 is also included, and it stops up at the value of 4. So my domain is from negative infinity to 4. The the range, I look from bottom up. The bottommost part of my graph is this piece of the horizontal line. Projecting it over, I see that has a y value of 1, and it is included in part of the graph, so I'm going to put a closed circle. And then there's a gap, right? As I move from bottom up, there's a gap, and I have another piece that has a bottom point at 2. And then that piece continues until I get to this top point of 8. So notice my graph is continued between these y values of 2 and 8, but the 1 is a distinct point. So the way we write our range is the set containing 1, then union the interval from 2 to 8. Example 4. Our leftmost point is at an x value of -2, and it's included there, so we're going to have a closed circle. And where does this graph end to the right? Well, our rightmost point is indicated by this arrow. Or infinity. And then every point in between, right, because the graph is continuous, it doesn't break between those points. And so our domain is from bracket -2 to infinity, close parentheses. For the range, I have to think about the bottommost point. And this is a little bit tricky because notice that I have, it looks like a bottom point here at -1. But notice that this piece to the right has an arrow, so whenever I project it down, it's going to continue indefinitely. So it actually goes below this value of -1. It does have a topmost point. The topmost point is 1, 2, 3, 4. And that's included in my graph, so I'm going to put a closed circle. So we really have a bracket at 4 continuing down to -infinity. So the range is -infinity to 4. Always write the range and domain from smallest to largest. The last few examples are going to be to determine the domain and range if you're given an algebraic function. The first two examples are polynomial functions. First one is specifically a linear function, f of x equals x plus 3. The second example is a polynomial function, f of x equals x cubed minus 4x squared plus 2x minus 1. Any polynomial function is defined for all real numbers. I can put a real number in, I can square it, multiply by a number, add, subtract, anything like that, and I'm going to get a real number output. So for polynomial functions, the domain is all reals. Or -infinity to infinity. I have here defined the range, but we're actually going to look at that more in detail later. Equation for our function. For a line, we can know that the graph of a line with slope 1 and y-intercept of 3 will continue indefinitely from left to right and also bottom to up. So the range of that would be -infinity to infinity. But let's hold off on finding the range for these till a little bit later. The polynomial you'd have to graph, and there's some key things that you need to know about those before we can actually get into precise methods to find the range. So here again, we'll just determine the domain for the function. If we have f of x equals x minus 3 divided by x minus 4, remember that a rational function is undefined for values that make the denominator 0. To find the domain, then, we have to exclude any value that makes the denominator 0. f of x equals x minus 3 divided by x minus 4. This function is undefined when x minus 4 equals 0 or when x equals 4. So the domain is all the real numbers except for x equals 4. So my domain would be from negative infinity to 4 with the parentheses, union, parentheses 4 to infinity. So the union just means that the set of x values can be in either piece of that for it to be included in the domain. For f of x equals x plus 1 divided by x squared minus 9, we know this function is undefined when x squared minus 9 equals 0, or where x squared equals 9, or where x equals plus or minus 3. So the domain is all real numbers except for plus or minus 3. If you draw a number line and take those numbers out, you'll see what is left. So everything to the left of negative 3, everything between negative 3 and 3, and everything to the right of 3. So we write this as negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. And our last example deals with radical expressions. So to find the domain of the square root of x minus 3, a square root is defined when the radicand is greater than or equal to 0. Right, if the radicand is negative, that gives us an imaginary number. So to find the domain, we have to set that radicand greater than or equal to 0. In this case, x minus 3 is greater than or equal to 0, or x is greater than or equal to 3. And that's everything to the right of 3, including 3. So the domain is 3 to infinity. This last example is a little bit more complex. It's f of x equals 3 divided by the square root of x minus 3. There's two conditions. We have to have first that x minus 3 is greater than or equal to 0 for the radical to be defined. But then we cannot have the square root of x minus 3 equaling 0 because that makes us divide by 0. So we know that x minus 3 is greater than or equal to 0 where x is greater than or equal to 3. The square root of x minus 3 is equal to 0 when just x minus 3 is equal to 0, or when x is equal to 3. So we're talking about here that x has to be greater than or equal to 3, but x can't be 3. So instead of including the 3 in our solution, we have to exclude it, which is designated by the parentheses. So the domain for this function is open parentheses 3 to infinity. Please let me know if you have any questions over finding the domain and range of a function from a graph or the domain given an algebraic function.